At high level, load balancing feels like a solved problem. We take a bunch of servers, we put a load balancer in front of them, and we assume it just spreads the request evenly across all of them. But here is the thing, let's say everyone got the same exact number of requests, and still one server is completely overloaded while the others are sitting idle. How does this even happen? Think about it carefully. Load balancing was never about spreading the number of requests. It was always about spreading the overall load on the servers. And those two are not the same. One request might be a tiny health check, another might be a 2-minute LLM answer. So, just counting requests tells us nothing about the actual load. So, let us build this up properly. We will go through every algorithm you have heard of, round robin, least connections, IP hash, one by one, and see exactly how each one breaks. And then I will show you the 4 questions that will make this whole list collapse into something we can just reason about. So as soon as we think about load balancing, the immediate one everyone thinks of is round robin algorithm. And the algorithm is something like this. We keep a small pointer and we just go through each and every server, serving the requests to them one by one. And when we reach the end, we come back to the top and start again. And it is genuinely nice. It is stateless. It is basically free. Just one counter. No coordination at all. For a pool of identical servers handling identical little requests, it works well. One small upgrade you will see is weighted round robin. Let us say one server is twice as powerful as the other. We give it twice the weight. So it gets 2 turns for every turn the smaller server gets. Same idea, just accounting for the difference in server capacity. But notice the assumption hiding in here. Round robin only knows whose turn it is. It has no idea what any server is actually doing right now. And that assumption that every request is basically the same is exactly where it breaks. If you think about it properly, the real requests are not always equal. One request might be a simple health check that takes a millisecond, another might be a file upload or a heavy aggregation or analytics query, or something like image generation. So the cost of a request varies a lot based on what kind of request it is. Sometimes 100 times, sometimes 1,000 times. So let us say one server catches one of these heavy requests and start to slow down. Round robin has no idea this is happening. So it comes back around and says your turn again and drops even more work on the one server that is already struggling. A lot of explanations tell that round robin is kind of less optimal, but it is much worse than that. It actually keeps sending requests to our slowest server because it does not have any idea about the current load on the servers. So all those quick little requests getting stuck behind the slow one and their latency shoots up. The average latency will be fine, but the P99, the tail latency, becomes really bad. So we cannot be blind like this. The balancer has to actually look at how loaded each server is. So one way to think about this, what if we know the number of requests each server is currently handling and we send the new request to whichever server has the least amount of requests. This is called least connections and it genuinely helps. A slow server piles up requests so it naturally stops receiving new ones. The load adopts on its own. But here is the catch, and this is the part a lot of explanations skip. Least connections always assume that we can see the load on every server. But at any real scale, we do not have just one load balancer. We have a whole row of them. And each load balancer only knows about its connections that it opened. It has no idea what the other load balancers are doing. So when each of them independently ask who is the least loaded server, they cannot look at the same idle server and all send it together. So least connections across a whole fleet is not actually the global least loaded. Each balancer is just guessing from its own small slice of information. So we have a real problem now. We want to send work to the least loaded server, but actually knowing that needs every balancer to constantly share the state. And that is expensive. And it is on the hot path of every single request. So how do we even find the least loaded server without actually knowing the load of every server? And the fix here is one of my favorite one because it is almost too simple. The core algorithm is something like this. When a request comes in, we just pick 2 servers at random. We only care about those 2 servers and we send the request to whichever one of them is less loaded. That is the whole thing. And it feels like this should not be enough, right? we are only looking at two servers out of maybe hundreds of servers. But there is a classic result from the 90s, the power of two choices. And it says that just going from one random pick to two gives us an exponential improvement. And here is the interesting part, going to three choices barely helps. It is only a tiny bit better than two choices. So, two choices is the sweet spot. That is why it is called the power of two. Two random checks, and we are already almost as good as perfect global tracker with no shade state, no coordination, and constant work per request. And this is not just theory, it is what the real systems actually run. Envoy at the equal weights has a mode called least requests that is exactly this. Pick two, take the one with the fewer active requests, and it has a really nice property. The most loaded server in the whole fleet will not get any new requests until it catches back up with the other servers. Nginx and HA proxy do the same thing. So if you take away one algorithm from this whole video, take this one. One small refinement because it matters a lot. When we say least connections, we are treating every connection as equal weight. But a connection to a slow, struggling server is not the same as a connection to a fast one. So the smarter systems in the world do not just count connections, they weight each server by how fast it has actually been responding lately. Basically, a rolling average of its latency. And latency here just means the time it takes for a request to complete. This is called peak EWMA. And for example, Twitter uses this. And usually they combine it with the two choices trick. Pick two at random, then take the one responding faster. Best of both worlds. So we went all the way from whose turn it is to two random servers. Which one is actually faster right now? That is the load question basically sorted. Now, two completely different questions that decide the whole shape of your setup. So far, I have been talking about the load balancer like it is a single thing, but there are actually two types of load balancers depending on how deep they look. So let us say you want to send all your image requests to a cheaper set of servers. Just keep that in mind for a second. The first one is called a layer 4 load balancer. It works at the connection level itself. It sees your IP addresses and the ports, and that's all. It does not know whether it's a web request or a database request. It just takes your entire TCP connection and forwards it. And because it's doing so little, it is extremely fast. This is your AWS network load balancer. That image request we talked about, a layer 4 balancer physically cannot see that you asked for images. It never reads up that far. The second one is a layer 7 load balancer. This one goes all the way up to the actual request. It reads the HTTP, the path, the headers, the cookies, so it can do things layer 4 simply cannot. Send image requests to one pool and API request to another. Handle your TLS, retry a failed request on a different server, and run those smart per request algorithms we just built. Because it can actually see your request, that is your application load balancer. The only cost is that it does much more work per request. And in real world, we do not pick one, we stack them. A fast, simple layer 4 tier in front, passing the connections into a smarter layer 7 tier behind it. Okay, a completely different requirement now. Sometimes we actually want the same client to keep hitting the same backend server. Let us say that server is holding the user's session in the memory or it has their data warm in its cache. If we spread them around, we throw all of that away. So the immediate move we can think of is hash the client and mod by the number of servers. That gives us their backend server, hash of client mod n. And if you're already recognizing this, this is a very good thing because it is the exact same problem we solved in the consistent hashing video. So what happens when we change n? One server dies or when we add one and almost every client now maps to a different server. Every session gone, every warm cache cold and all at once. It is exactly the same thing we saw with naive hashing. Just now it is with load balancers instead of databases. And the fix is the exact same fix, consistent hashing. We put the backends on a ring, we walk clockwise, and now adding or removing one server only moves about 1 in n of the clients. Everyone else stays exactly where they were. Envoy even has a setting for this called ring hash. So the same ring we learned for databases, it is also how a load balancer keeps its connection stable. None of this matters if we keep sending the traffic to a dead server. So the balancer is constantly checking the health of the each server, either actively by pinging a health endpoint or passively by just watching the real requests and noticing when a server starts timing out or throwing errors. Either way, the moment a server looks dead, we take it out of the rotation. Otherwise, least connections happily keep sending requests into dead server because a dead server has zero connections, so it looks like the least loaded one. But here is the sneaky part, the recovery. The server goes down and then comes back, and it marks itself healthy. And the moment it marks itself healthy, it immediately receives a huge load of requests all at once and it just breaks again. So the fix is simple. We do not give a fresh server the full load immediately. We ramp it up slowly. This is called slow start. And we give it 10% of the traffic first, then a bit more, then more, as it proves it can handle the load. And honestly, this is the same thundering head problem from the rate limiting video. Everyone rushing the recovered server all at once. A little ramp up, a little jitter, and its server is coming back. So there is one obvious question here. Everything is going through this one load balancer. So is the load balancer itself not a single point of failure and a bottleneck? If it goes down, the whole site goes down, right? So the real answer is we do not have just one. The network itself, using something called Anycast and ECMP, sprays the incoming packets across a whole set of identical layer 4 boxes and all active at the same time. One of them dies, the others just absorb its share. No failover drama. But this raises a subtle question. If the packets of the same connection can land on different boxes, how do all the boxes agree on which backend that connection belongs to? And the answer is close to the ring. Every box hashes the connection in the exact same deterministic way. So they all independently land on the same backend. No communication needed between them at all. Google's version of this is called maglev. And this is the thing people get wrong. Maglev is not quite the consistent hashing from the database video. It is its own algorithm. It is tuned to spread the load really evenly, and to do that, it trades away a little bit of stability. Its lookup tables build much faster than a classic hash ring, something like 10 times faster. But when a server leaves, roughly twice as many connections move compared to the ring. So, deterministic like the ring, faster but a little less sticky. Meta and Cloudflare run their own versions of the same idea right inside their kernel. So the full front door is just layered Anycast into a simple layer 4 tier, into a smarter layer 7 tier, and then onto your actual backend servers. And I want to end on where all of this is going because it is close to home for me. Load balancing for LLM inference. It takes everything we just talked about and pushes it to the extreme. Think about this in terms of an LLM running on a GPU. If we use round robin here, one request might be of 50 tokens and another might be of 50,000 tokens. And if we pick servers in round robin way, the server that gets the 50,000 token request takes a very long time and gets loaded because it cannot return the response quickly. And all the requests behind it just pile up. And here is the surprising part. A lot of these systems still default to round robin, even NVIDIA's own inference router does by default. So this is a very live problem right now. So what does the better serving systems do? They look at each other's worker queues. How much is it already running and how much is waiting? And they send the new request to the shortest queue, which is exactly the least outstanding requests. Join the shortest queue. The same idea we built for web servers, now deciding which GPU gets your prompt. And the sticky routing idea shows up here too, in a beautiful way. These models keep a big chunk of state for each conversation. It is called the KV cache. So if a worker has already processed the start of your prompt, we want to route you back to the same worker so it can reuse that work. So they score each worker on how much of your prompt is already has cached and use that as a stickiness signal. And the payoff is real. Cache aware routing roughly doubles the throughput. And when there is a lot of shared prefix, it can cut the time to first token by a very large amount compared to plain round robin. So, least outstanding requests plus cache affinity stickiness, the same two ideas from this entire video, now running the most expensive computers on the planet. So we covered a lot of algorithms and the trap. The thing every other explanation does is to hand you exactly that. A big list to go and memorize. Round robin, weighted, least connections, IP hash and so on. Do not do that. Because at high level, we are really only answering 4 questions and the algorithm just falls out of the answers. 1. Layer 4 or layer 7. Do we just forward a connection quickly or do we read the actual request and route on it? Number 2, stateless or sticky. Does a client need to come back to the same backend If yes, that is a consistent hashing the ring. Number 3, and this is the heart of it. How do we send work to the least loaded server when we cannot afford to know the load of every server? And the answer is almost never track anyone. It is pick two at random and take the better one. Number 4, how do we stay stable when a server dies or comes back? Or we add one, health checks, slow start and again the ring. So that churn only moves one in n. Answer those four, and every algorithm on that list just slots into place. And the one line to remember the whole thing is this: we are not spreading requests, we are spreading load. And that is the important part. The beautiful thing is, we do it with almost no information because two random guesses actually beat a perfect tracker that we could never afford to build.